everyone. Today we're going to be talking about carbon organic soil. I'll start by introducing what soil organic carbon is, its relationship with climate change, and how to monitor soil organic carbon. So what is soil organic carbon? Soil organic carbon is the carbon that remains in the soil after partial decomposition of any material produced by living organisms. It constitutes a key element of the global carbon cycle through the atmosphere, vegetation, soil, rivers, and the ocean. Carbon storage is an important ecosystem function of soils. Soil is a major carbon reservoir that holds more carbon than is contained in the atmosphere and terrestrial vegetation combined. All three of these reservoirs are in constant exchange. The major input of organic carbon to soils is provided by the uptake and fixation of carbon dioxide by plants, and by the incorporation of plant residue carbon into soil. Carbon additions from off-site sources, such as compost and manure, may also occur. Some of the fixed plant carbon may be removed by harvest before entering the soil. Organic matter on and in the soil is subject to mixing by soil fauna and to enzymatic breakdown and metabolism by microorganisms, resulting in the release of carbon dioxide from microbial respiration. Factors controlling the decomposition of organic matter in soil include soil temperature and water content, which greatly influence soil carbon storage through their effect on microbial activity. Erosion can also directly affect the soil carbon balance through the removal or deposition of the carbon contained in the transported soil. Leaching of dissolved organic carbon and dissolved inorganic carbon through the soil profile and out into groundwater and surface water represents an additional loss pathway that can be significant in some soils. Soil organic matter contains roughly 55 to 60% of carbon by mass. In many soils, this carbon comprises most or all of the carbon stock and is referred to as soil organic carbon. Soil organic matter is composed of plant litter compounds as well as of microbial decomposition products. It is critical for the stabilization of soil structure, retention and release of plant nutrients, and maintenance of water holding capacity, thus making it a key indicator not only for agricultural productivity, but also environmental resilience. The decomposition of soil organic matter further releases mineral nutrients and makes them available for plant growth. Soil organic matter can be divided into different pools based on the time needed for full decomposition and the residence time of the products in the soil, otherwise known as turnover time. Due to microbial degradation and mineralization to carbon dioxide or methane, the majority of plant litter compounds added to soil remain for a relatively short time, from a few days to a few years. This is known as active pools, and is particularly the case if organic compounds are added on the soil surface. In passive pools, some organic matter compounds can persist for decades or centuries or even for millennia in the soil. Longer-term stabilization is generally conferred through interactions with soil minerals that reduce soil organic matter exposure to enzymatic degradation. These interactions include incorporation of soil organic matter components into soil aggregates, attachment of organic matter to protective mineral surfaces, the spatial disconnection between soil organic matter and decomposers, and the intrinsic biochemical properties of soil organic matter. Microaggregates are considered responsible for the stabilization of the passive pools, whereas macroaggregates are considered transient stabilizing agents. The physical and chemical stabilization of soil organic matter hinders microbial decomposition via restricted mobility and access of microbes to organic matter, as well as diffusion of water, enzymes, and oxygen. In addition, such stabilization requires a broad range of microbial enzymes to degrade the insoluble macromolecules that comprise of soil organic matter. Soil carbon is usually divided into a number of pools in order to represent the heterogeneity and residence time of the vast mixture of different organic compounds in soil. The fast or labile pool represents easily degradable plant material, microbial biomass, and labile metabolites, and may turn over within a few months or years. The intermediate pool comprises processed organic matter that is partially stabilized on mineral surfaces or protected within aggregates, with turnover times in the range of decades. The slow or refractory pool, including highly stabilized organic matter mineral complexes and pyrogenic carbon, can remain in soils for centuries or millennia. Soil can either be a net sink or a net source of greenhouse gases. As a source, soil emits greenhouse gases into the atmosphere where they trap thermal radiation that enhances the greenhouse effect and contributes to global warming. The carbon-based greenhouse gases emitted by soil are carbon dioxide and methane, which are two of the most leading anthropogenically emitted greenhouse gases. Another form of greenhouse gas is nitrous oxide, the emission of which has become increasingly anthropogenically driven, largely from agricultural soils and livestock facilities. The inclusion of all three gases in soil carbon dioxide budgets is important due to the interconnectedness of the processes involved in their emissions and ecosystem cycling. Carbon dioxide is the most abundant carbon-based gas in the atmosphere. In soils, carbon dioxide released to the atmosphere occurs when organic residues or soil organic matter are oxidized. The flux of respired carbon dioxide by soil fauna and below-ground roots from the soil to the atmosphere is referred to as soil respiration. It represents the second largest terrestrial carbon flux. Soil respiration is seasonally variable since it is controlled by environmental factors such as temperature, moisture, soil nutrient content, and oxygen concentration. Methane is released from soils through a process called methanogenesis, which occurs during decomposition of organic matter under anaerobic conditions. In such environments, methanogens, the leading form of bacteria that produce methane in addition to acetate fermentation, utilize carbon dioxide instead of oxygen as a final electron acceptor for metabolic activities, releasing methane as a byproduct. Thus, waterlogged soils, particularly wetlands, peatlands, and rice paddies, are the largest source of methane emissions. Under aerobic conditions, methanotrophic soil bacteria thrive and use methane as a source of carbon in a process called methanotrophy, which oxidizes methane. As such, forest soils tend to be good sinks for methane due to their low water table that allows these bacteria to grow. The water table level is considered a key to whether a soil can act as a sink or a source of methane. Nitrogen and temperature are also noted as determinants of a soil's carbon sequestration potential, since they regulate the amount of methane emissions. Soil organic carbon sequestration is the process by which carbon is fixed from the atmosphere by plants or organic residues and stored in the soil. When dealing with carbon dioxide, soil organic carbon sequestration involves three stages. The first is the removal of carbon dioxide from the atmosphere by plant photosynthesis. The second is the transfer of carbon from carbon dioxide to plant biomass. And the third is the transfer of carbon from plant biomass to soil, where it is stored in the form of soil organic carbon in the most labile pool. Newly added carbon can be stabilized in the soil by a number of mechanisms. Physically, carbon may be stabilized by its isolation inside soil micro and macro aggregates, where it is inaccessible to soil organisms. Chemically, carbon may be strongly absorbed to clays through chemical bonds, which prevents the consumption of carbon by organisms. Biochemically, carbon may be resynthesized into complex molecule structures that may hinder decomposition. The three mechanisms depend on a number of biotic, abiotic, and management factors that shape their soil carbon stabilization efficacy. The concept of soil carbon saturation implies that the soil carbon stock has reached its maximum carrying capacity for storing soil carbon inputs. This threshold, which depends on many factors, including inherent and dynamic soil properties, and their interactions with abiotic factors, is also known as the maximum carbon stabilization capacity. It infers that soil carbon stabilization curves are not infinitely increasing, and that when a carbon saturation level is reached, soil organic carbon sequestration comes to an end. Soils stop being a net carbon sink and can become a net carbon source instead. As such, soil organic carbon sequestration has spatial and temporal limitations and is a reversible process. Soils that are depleted of soil organic carbon have the greatest potential to gain carbon, but also have the least tendency to do so. Since the majority of soils around the world are far from their saturation thresholds, there is a great potential for increased carbon inputs and management that protects existing stocks to maximize soil carbon sequestration. In general, carbon cycling and carbon sequestration is most active in topsoil horizons, where stabilized carbon with longer turnover times makes up a greater proportion of the total soil organic carbon found in deep soil horizons. Soils at greater depth have a higher capacity of storing additional carbon compared to topsoils, because of a larger difference between the existing soil organic carbon content and the soil organic carbon saturation value. The accumulation of stabilized carbon with long residence times in deep soil horizons may be due to continuous transport, temporary immobilization, and microbial processing of dissolved organic carbon within the soil profile.